Hello and welcome to the Advanced Rocketry Club High-Powered Rocketry Certification Info Session. So brief overview. We'll start off with kind of why you should get certified for high-powered rocketry, the different rocketry associations that exist in the US, and how to get involved in them, different kits that are available to build and fly your level 1 rocket. And if you want to design it from scratch and build it that way, I've got some information on how to do that, as well as motor selections, and finally the flight card that we'll all have to fill out before going out to launch. So getting started with kind of why you should get certified. Certification allows for the private purchase of higher impulse motors. So you don't need a certification to purchase impulse class A through G motors. However, any higher and you will need to start getting your certification levels. So level 1 allows you to purchase H and I, level 2 J through L, and level 3 M through O. Additionally, getting your high-powered rocketry certification allows for hands-on launch experience with high-powered motors, something that we'll do plenty in this club. But if you're interested in that as a hobby, which if you're in the club already, why not? It's a really fun hobby. There's a lot of cool people involved in it. You can do a lot of really cool things with some of the higher impulse motors, doing your own experiments, going to different rocketry events. Recently, there was Balls 32 down at Black Rock. That one's a good one, open to the public. There's NARM associated with the National Association of Rocketry. Tons of different competitions and events that you can go to nationwide. So a little bit about the different rocket associations that you can get your certifications through. There are two rocket associations located in the US, the National Association of Rocketry, or NAR, or the EEE Rocket Association, or TRA. So NAR is a little more strict on safety and rules and buying commercially purchased, verified rocket motors in order to be a NAR-sanctioned launch event. They don't really like the experimentation part of rocketry as much, so they're going to be a little more stricter. They do run the NASA Student Launch event down in Huntsville, Alabama. That's one of their main events that they help put on with students. They also have NARM for hobbyists and amateurs all around the world, or all around the US. Membership fee for NAR is $30 for students. That does include a magazine, so you get some pretty fun articles in there talking about rocketry. And that is $30 per year. The EEE Rocket Association, they allow for a bit more experimentation, so mixing and testing your own rocket propellants, that kind of thing. You're still covered under that EEE insurance, which is very helpful. Membership fee for EEE is currently at $20 for students. There's no magazine with EEE though. And I do have to check whether or not our advisor can certify level 1 for EEE. I know for sure that he can with NAR, but I'm not sure if he's went through the process of getting his level 2 acknowledged by EEE quite yet. So I'll send out an update on that later once I get that information. But these, you're going to need to be a member of one of these to certify. It will have you fill out an info card on your rocket and have a certified member of one of the organizations present to verify your launch, and then we'll submit that to the organization, which you'll then receive your certification card. And once you are a member of one of these organizations, you are covered under their insurance. So as long as you follow the proper launch procedures and safety guidelines that each organization puts out, you are covered for up to $3 million in damages. So that is extremely helpful, especially if a rocket happens to go through a car window, which never happened to us, but NASA did it. We'll blame NASA. So a little bit about the certification rocket kits. There are tons of kits out there that can be purchased and assembled. You don't have to do all the design work and simulations and analysis on it to make sure that it works, all that. You can just purchase a kit, put it together. It's very easy, but still very hands-on and very fun to do. So those are available from multiple different sources, the main ones being Wildman Rocketry, Lock Precision, and Apogee Rockets. So most of them have a filter option to search by level 1 certification rocket kits. Some you'll have to kind of sift through and look in the description of each kit to see whether or not they classify for a level 1 cert or not. Some can be modified to technically classify, but as long as you can fit an H or an I motor in there and fly it safely, it pretty much classifies. Some kits double as level 1 and level 2 certification rockets. So after you fly your level 1, you can take it back, refurbish it, outfit it for a dual deploy, take your test, and then fly again to receive your level 2 certification. So I've got the links there to the different lists of certification kit rockets on each website. This presentation is available in our Teams and will be available on our Notion page as well. I know a lot of you have already taken a look at these, but just having that nice quick reference guide right there is helpful. Now, if you want to design your rocket from the ground up, that is also highly encouraged. You get a more intimate knowledge of how the design of a rocket works, what each design criteria influences in the overall design. This is something I did for my level 1 and for my level 2. So there are a few different materials you can choose from when designing your rockets. So I'll start off by going through body tube material options. The main one used for level 1 rockets is going to be cardboard. It's very light, very easy to work with, but it does degrade over time, but it's also cheap. So there's plenty of advantages, but a few disadvantages as well. So if you're going to want to keep it around, do multiple flights, that cardboard is not going to hold up the same after each flight. If it hits the ground pretty hard, you might need to replace a whole section of the body. But it's super cheap to get into, super lightweight, and especially for a level 1 certification, you don't need something super strong since it's only an H or an I motor. Level 2 rockets can even fly with cardboard pretty easily. The next step up would be something like phenolic. It's a little, still lightweight, but a little heavier than cardboard. PPE would be required to work with it since cutting phenolic and releasing that dust can be toxic. But it's going to be a little more rigid and hold its shape a lot better over time, but a little bit more expensive than just a plain cardboard tube. Fiberglass has been a mainstay for a long time in the club. Most of our competition rockets in the past have been commercially purchased fiberglass body tubes, and most of our NASA student launch rockets have flown on a level 2 motor. So it's tried and tested for level 2. It's a very good material. It's a little heavier, still very lightweight though, especially with the strength to weight ratio. It's going to be a lot harder than cardboard and phenolic, and it's going to take a lot of hits very easily. PPE would be required to work with it since you don't want to breathe in any fiberglass or get that lodged in your skin while working on it. It can get kind of itchy. Trust me, it's not fun. Again, the fiberglass lasts quite a long time, so if you want to keep your rocket around for years and years, it's not going to degrade. It's not going to absorb moisture and sag and lose performance over time. As it's going to keep its shape and keep its structure pretty well. And the next step up from fiberglass would be like a carbon fiber. It's a good medium weight. It's got the best strength to weight ratio out of the listed materials. PPE would be required to work with it. Again, you don't want to be breathing in microcarbon slivers and getting those lodged in your lungs. That's not something we encourage. It can be a little bit more expensive to buy, so if cost is a factor, I'd probably steer you towards a cardboard or a phenolic, especially for level 1 and level 2 certifications, or a fiberglass. Fiberglass is a little bit more on on the pricey side, but again, it's going to last a long time. And if you're going to do multiple flights with your rocket, it's well worth it in my opinion. Now, moving on to the nose cone, there's a few different materials out there that you can purchase. So one of the common ones for level 1 and level 2 certification rockets, kind of anything 4-inch or smaller, is going to be like a uh, plastic molded nose cone. These are cheap, they work very well, they're tried and trusted, although they cannot handle high heat / speeds. So once you get up to close to Mach 1, so like Mach 0.7, around there, you're going to have a decent amount of surface heating on your rocket, and plastic can warp under those heats depending on how fast you're going. So it's not really recommended for super high speeds. So if you're wanting to build a fast, high rocket, something like a fiberglass or carbon fiber would be a lot more suggested. Which brings us to the fiberglass. It is heavier. So if you've got a cardboard body tube, but a fiberglass nose cone, that's going to shift your center of gravity up farther to the nose cone, which can be beneficial since you want to keep your stability margin kind of between that 1.5 to 3 caliber ratio. It performs very well under high heat and high speeds. Some of the commercially purchased fiberglass nose cones are a hybrid composite with fiberglass and carbon fiber. This improves the heat capacity of the material, so it really performs well. A lot of them also have an aluminum leading tip, which is good for aerodynamics and that heating issue, so you're not buckling, and you can have that nice sharp pointy rocket. Now, if you want to go a little bit more custom, you can 3D print your nose cone. So you can get a custom shape. It prints for cheap. You do have to factor in the design and print time for that kind of nose cone though. And like the plastic molded, it's not going to perform very well in high heat. So you want low heat and low speeds to really get the best performance out of it. One issue with 3D printed ones is delamination. So delamination is a common issue with most structural 3D printed parts. You have to kind of design around the possibility of delamination. So that's where these layers can just separate from each other. That's going to be your major weak point in any 3D printed design. But again, at those low speeds and low heat, it really performs pretty well. I personally did a 3D printed nose cone for my level 1, and it is still in perfect condition. Now moving on to the fin materials. Plywood is a really good, really cheap material to use for a lot of lighter rockets. You can get some pretty thin plywood sheets to cut out and make your fins. So that's what a lot of those kits come with. It's easy to work with, and downside, it can be heavy depending on the thickness of it. It doesn't have as good of a strength to weight ratio as something like fiberglass or carbon fiber, but it is a very good material to work with. However, if you're going to be experiencing a lot of torsion forces on your fins or getting high speeds, high fin flutter, a fiberglass fin is going to be a lot more rigid. So it is a little harder to work with. PPE is again required for any fiberglass cutting and manufacturing, but it's got a lightweight and high strength, so that really improves the performance of your rocket. You can have a thinner fin with just as much strength as a thicker fin would be out of plywood. So you're reducing the leading edge surface area, reducing that drag, so you can have better performing rocket. Now, if you're doing a minimum diameter, it is highly recommended, basically required that you do a fiberglass layup on it, depending on the speeds. So a fiberglass layup is where you take a sheet of woven fiberglass, cut it to the shape of the fin that you want, and you lay that up on top of your fins from the tip of one fin down to the body, over the body, and up to the tip of the next fin. And then that is saturated with epoxy and let cure. So that really really increases the strength of the fins. We did this for our Perception rocket, which we flew in New Mexico last year. We did a 7-layer fiberglass layup. This increased the strength so much that it could go sideways at Mach 1 and not tear itself apart. So I would say 7 layers is probably excessive for any level 1 or level 2 rocket. Anywhere between 1 and 3 layers is probably going to be optimal for any of you who are wanting to do a minimum diameter, high speed rocket.
Is that the kind of fins that I stood on and broke?
Yes, that you stood on a 3-layer and broke it, but you also stood on another 3-layer and did not break it.
Okay.
Yeah, you could stand on the fins of Perception and they would not break. I'm very confident in saying that. So moving on to parachute selection. When selecting your parachutes, you're going to want to run multiple open rocket simulations to determine the optimal descent rate and landing velocity. So one thing with descent rate, you don't want it to take forever to come down. That's why typically for a dual deploy, we release a smaller parachute at apogee to just gradually reduce the descent rate, and then a larger parachute down lower where we get our final landing velocity. Because if we let it have that landing velocity all the way down, it's going to drift a long ways, and we're going to no longer be the advanced rocketry club and more of the advanced hiking club. And that's not what we signed up for. So we tend to follow the rule of keeping 75 foot-pounds of impact force as an upper limit. We find this by using the kinetic energy equation. Kinetic energy is equal to 1/2 mass times velocity squared. So we just plug that into the plug our landing velocity into for that v in that equation and the mass of each component of our rocket in for m, and we'll get a different kinetic energy for each part of the rocket. Since they are separate things hitting the ground at different times, they're going to have different kinetic energies. But yeah, you don't really want to go above 75 foot-pounds of force. Even that's a little high. I don't foresee any level 1 or level 2 rockets seeing that unless you're coming down ballistic. To see what parachutes we have available, check our Notion inventory page. It's located right under ArcHQ. On the sidebar, there's an inventory, and then you can see all the different parachute sizes that we've got. If you want a better idea of drag coefficient, you can look on Fruity Chutes. They've got a lot of different parachutes. We've got a few from them. Most of them have a drag coefficient of around 2.2. So that's a pretty good estimate to plug into OpenRocket to get a good simulation. Now, when selecting your shock cords, as a rule, we like to keep them between 2 to 3 times the length of the rocket. This keeps any sections from hitting each other on the way down, because you don't want your rocket to separate and then on the way down your nose cone section and your fin can are just smashing into each other, because that'll cause damage. We've had that happen in the past where they've scraped by each other. We did follow the 2 to 3 times length rule, but it still can happen, especially if they're just passing by each other in air and smack into each other. It's a risk. We kind of have to accept it, but typically 2 to 3 times is what the community recommends. And again, shock cords are on our Notion page under the inventory, so you can look through to see what we have. If you're designing your own level 1, then you might want to talk to a few other people who are launching that day to make sure you're not selecting the same shock cords, or if you are, that one of you goes first, and then after recovery, you can take those shock cords off and share them with the next person to launch. We've had to do that with altimeters before because we're a little limited. And I just wanted to show my certification rocket designs from OpenRocket. So on the top here, that's my level 1. I went with a fiberglass body tube launching on an H100 motor. It reached an apogee of 914 feet. I did a 5-fin design since we were competing in the Minnesota rocket competition. And they required a fun little design feature. So mine was 5 fins with a really far back, really large sweep angle. So that's why they're extending so far back behind the rocket. Typically, that's not recommended because as it's coming down, those fins are going to be the first thing that hit the ground. And if they're so far back, it's a high likelihood that they're going to break. So I reinforced mine with a lot of epoxy right next to the body of the rocket in order for that not to happen. Luckily, it didn't. My rocket's fine, it's intact, it's in my living room, it can be flown again. And then on the bottom here, I've got my design for my level 2 rocket. This is still underway, it's still getting worked on, but hopefully I'll be able to get it done and finished by November 9th to launch at our certification launch. So this one is another fiberglass body. It's a minimum diameter rocket launching on a K550. Its predicted apogee is 11,000 feet currently. I'll be launching a dual deployment system, so I'll have a drogue and a main chute in there. And I've also worked in a boat tail design on the aft end of the rocket. So that boat tail reduces drag and lets me go higher faster. So a little bit about motor selection. So when you're designing your rocket, even if you're getting a kit, you're going to need to select your own motor for it because the kits won't come with a motor. So for level 1, you need to select either an H or an I motor to certify. There are some lower impulse class motors that are technically level 1 because of the amount of impulse they have, but that's kind of rare. So typically an H or I motor is pretty consistent. One thing that I would recommend doing for level 1 especially is going with those single-use motors with a delay grain. Because then you can use that as your ejection charge and you won't need to put any electronics on it. There's no harm, no foul if your rocket goes ballistic and smashes into the ground. There's no electronics that's going to break. Um, so with that, most of those motors come with a delayed grain. So typically they're around 14 seconds. Then you drill out the delay to reach that optimum delay time. So in OpenRocket, it'll tell you a value called your optimal delay time. That is the delay on your grain that you're going to want. Um, that delay is the amount of time after ignition that your charge goes off and your parachute separates from your rocket. You want that to be pretty much exactly at apogee, because if you're either before apogee or after apogee, your rocket has velocity. And when your rocket separates with velocity, there's a lot of force on that parachute, a lot of force on your rocket, and that can really damage components. So when looking for a motor, motors are categorized by impulse class and diameter. So they'll have H and then a number following. The H is the impulse class, the number following is the impulse, and then the diameter is listed later. So like an H100, that's a 38 millimeter diameter motor. So that would fit any 38 millimeter rocket body tube. You're going to want your motor mount tube to match the motor's diameter. Otherwise, bad things will happen, or you'll just not be allowed to launch. For a level 2 certification, a J, K, or an L motor is required. L's can start getting pretty expensive, so K is kind of more the upper limit without getting too pricey, I would say. But most of these sizes, K and later, are reloads that require a separate motor case. So this is an aluminum casing that we load the grains into. We do have quite a few of these, so if you want to use a reloadable motor, check with us, see if we've got one of those cases available. We might be able to borrow one of those out to you as long as you promise not to lose it, because those are very expensive. For more detailed information about motors that you want to select, go to thrustcurve.org. That has all of the necessary information for your motor, as well as the actual thrust curve, which is great. If OpenRocket for some reason doesn't have your motor in its category uh, or catalog, then you can import a file that you download from ThrustCurve uh, into your OpenRocket path, and then you just select where it should search for that, and then it'll pull that up and import it as a new motor. So that's a really great feature of OpenRocket, but typically it's got just about all the motors you could want. All right, so a little bit about the flight card. So this is a new thing that we're introducing to the club after last year. Anyone flying their rocket will be required to fill out our flight card. This has a ton of need to know information on your rocket. This proves to us that you know your rocket and you know what it's going to do. Majority of this information can be found from OpenRocket or taking direct weights. For the weights and lengths, typically it's recommended that you do take the actual measurements from the physical thing and then use that information to update your OpenRocket and get a more accurate simulation. Um, there's a few things on here that might not particularly apply to you, uh, such as some altimeters. If you're not flying with an altimeter, just write NA. If you're only flying with one altimeter, under secondary, just write NA. But pretty much everything else will correlate. Under weights, if there's a section in there that you don't have, just again, write NA. Yeah, this flight card will then be sent out to everyone who informs us that they are flying on November 9th, or any future launches for that matter. And we will expect them to send us the filled out copy of this or have it on them the day of flight in order to show us that you know all the key information about your rocket. All right. Well, thank you for listening to this talk. If you have any questions, now is the time for them.
How do you see where the optimal deploy thing is on OpenRocket? Or yeah.
So on OpenRocket, here I'll pull up my level 1. So under flight simulations on the top here, you have your different simulations that you go through. It's got which motor you've got configured in it. It's got key information such as velocity off rod, apogee, velocity at deployment, and then here is your optimum delay. So here I'll just run a simulation. Here it's saying my optimum delay is 7.97 seconds. So that's what you're going to want your grain delay charge to be.
So mine says 9.98, and the one I was looking at is 14 seconds. Is that changeable, or is that fine, or what should I do with that?
Yep, that 14 seconds is decreasable. However, it is not increasable. So you want your optimum delay to be less than 14 seconds, or equal to or less than 14 seconds, because what we'll do is we'll drill out a select amount of that delay grain, and that will specify the time delay to what you want it to be.
And do we already have the tool for that, I'm guessing?
Yep, we've got that.
Sounds good.